Welcome to the first part of the problem-solving session for Chapter 33. Let's begin with question 1. Here, question 1 is a two-part question. In fact, it's two separate questions, but they were placed on the same slide. The first part says, will a transformer operate if a DC battery is used for the input voltage across the primary instead of an AC generator? Well, the answer here is that no, the DC battery is not going to create a changing flux that is going to induce a current, a voltage through the secondary. So a transformer does not operate with a battery since it requires a change in the magnetic flux in order for an induced voltage to occur on the secondary side. Since batteries never change in voltage terminals, the current direction does not change. Neither does the value of the current, because a battery supplies a constant voltage. Thereby, nothing changes the flux on the secondary side and nothing is induced on the secondary side. So transformers can only operate based on Faraday's law, which requires that a changing magnetic flux induces a voltage on the secondary side. Now, for the problem, we're told that a step-down transformer, okay, that means that the voltage through the secondary side will be lower than the voltage through the primary. A step-down transformer is used to recharge the batteries of a portable tape player. The turns ratio is 1 to 13. Remember, that is NS over NP. And it is used with a 120 volt RMS household service. Now, because the transformer is part of the plug and the plug plugs right in to the household service, the 120 volts is said to be the primary. So delta V primary RMS is 120 volts. Now we're told NS over NP is 1 to 13. So in fact, this confirms that it's a step-down transformer because this will be a number less than 1. And we're told that the transformer draws a current 0.35 amps from the house outlet. Well, here again, they must have given us I primary RMS because the house outlet is the primary side. So we have 0.35 amps of current on the primary, 120 volts of voltage on the primary, and then NS over NP, that's 1 divided by 13. They ask us to determine the voltage and the current supplied to the tape player. And here, although they haven't specified RMS, since we've been given the values as RMS, we're going to solve for the secondary, delta V secondary, as an RMS quantity. Of course, we could easily multiply this number that we get here by square root of 2, and that would give us the primary, the maximum on the secondary side. Okay, so delta VP RMS times NS over NP, and of course NS over NP is times 1 divided by 13. So whereas the primary we've been given as 120 volts, we multiply that by 1 divided by 13. In other words, we can divide it directly by 13, and that gives us a voltage of 9.23 volts of RMS on the secondary side. Now for the current I secondary RMS, we do just the opposite. We take I primary RMS, and instead of multiplying it by NS over NP, we multiply it by NP over NS. In other words, 13 divided by 1. And now we plug in our values, 0.35 amps times 13, and that gives us a secondary current with an RMS value of 4.55 amps, if my calculations are correct. And so you can see clearly that when the voltage on the secondary side is reduced by 13, the current on the secondary side is increased by 13. The last part of the question asks us to calculate the power which has been supplied across the transformer. The average power we can calculate in two ways, either I secondary RMS times delta V secondary RMS, or we should equally get the same value, because remember that power is conserved, I primary RMS times delta V primary RMS. And so let's plug in our values, and you can take a moment to check for the secondary to make sure we get the same values. 0.35 amps of the primary RMS times 120 volts on the primary of RMS gives us a wattage of 42 watts. So 42 watts on the primary side, 42 watts on the secondary side. If they had given us the value of resistance and asked us what is the power which is consumed by the resistor, then that quantity would be I secondary RMS, since that is what goes to the resistor, squared times the resistance. But they didn't give us that, so we don't have to worry about this at this point. Next question. Question 2 again is a conceptual question, like the first part of question 1. It says fluorescent lights flicker on and off 120 times each second. Explain what causes this and why we don't see this. Well, it's a very simple explanation, and that is that the frequency at which most household that FPL transmits, and therefore most household receive, is 60 hertz. So this is the frequency of the generators that FPL uses, and in fact, throughout the country we use 60 hertz. And if you recall from our lecture, we said that there are 2 changes to the current per cycle. 2 changes per cycle. But here, this is 60 cycles per second. So 2 changes per cycle times 60 cycles a second equals 120 changes per second. Well, that's what we were told here. Now we understand what causes it, but why don't we see it happening? Because our eyes are unable to detect changes that occur this rapidly. 120 changes in 1 second is not detectable in human vision. Next question. Next question. Here we're told that the output voltage from a generator is given by voltage as a function of time equals 200 volts. And of course, don't forget that this is our amplitude, so this is our delta V max, times sine of omega t. The generator is connected to a resistor of 100 ohms. We need to find the RMS voltage, the RMS current, the average power consumed by the resistor. So let's start out with the RMS voltage. Now, before we do that, let's recall that the instantaneous voltage through the resistor is the same as the instantaneous voltage that the generator supplies. And so because the generator supplies this, the voltage through the resistor is the same. So with delta V max of 200 volts, we can then calculate the RMS value as the maximum, 200 volts, divided by the square root of 2. And that gives us a value of 141 volts. But I'm going to go ahead, because we're going to use this quantity in the next step. I don't want to introduce too many rounding errors. The actual result is 141.4, so I'm just going to leave it in this form. To get the RMS current, we're going to use Ohm's law here, delta V RMS, and of course we know this is through the resistor, so we don't have to keep putting the sub R for resistance, divided by R. 141.4 volts divided by 100 ohms gives us 1.41, and I'm going to add the 4 here again to avoid rounding errors for the third part of the problem. The third part of the problem, so we've got A, B, C. We're asked for the average power consumed by the resistor. Well, here IRMS squared times R will give us the average power. So 1.414 squared times 100 ohms gives us 200 watts. Next question. Oops, I think we skipped one. Here we're told that, in fact, I think we skipped more than one. Let's come over here. Yeah, we made a little bit of a jump there. In question 4, we're told that there is a purely inductive AC circuit. Well, what does that mean? Well, purely inductive AC circuit means a generator and an inductor only. Okay? The inductor has a value of inductance of 25 millihenry. The voltage that the generator supplies, which will also be equal to the voltage through the inductor, and here this is RMS, so this is sub L. The frequency of the generator is 60 hertz. We're asked to find the inductive reactance. Recall what that means. You want to get used to these words. Inductive reactance is X sub L. And the RMS current through the circuit, well, since we only have an inductor, it will be the current, the total current, which is the same current that the inductor is going to have as it tries to oppose the changes in the circuit. Now, X sub L, of course, is given by omega times L, but we weren't given omega. However, there is a direct relationship between omega and F. That is, omega is 2 pi F, and that we're going to multiply by L. So 2 pi times 60 hertz, the frequency of the generator, times 25 e to the minus 3 Henry, and that gives us an X sub L value of 9.42 ohms. Of course, that's provided we put in all our numbers correctly into the calculator. The next part asks us to determine the RMS current through the circuit. Well, that's going to be delta V RMS from the generator, which is the same as through the inductor, divided by X sub L, because here we're using Ohm's law to get the value for the IRMS. 150 volts divided by 9.42 ohms gives us a current of 15.9 amps. Next question. Here we're given a purely capacitive AC circuit, and again, this means only a capacitor and a generator connected to each other. This time we're given the capacitance as 8 microfarads, connected to the same, obviously, generator as the previous question, an RMS value of 150 volts. The frequency is 60 hertz. Capacitive reactance, again, that term indicates X sub C, and I RMS through the circuit, which is the same as through the capacitor. X sub C this time is 1 over omega C, but omega, recall what we just said, is 2 pi F times C. So we enter our quantities here, 1 divided by 2 times pi times 60 hertz times 8 e to the minus 6 farad. And when we plug that into our calculators, we get 331.6 ohms, or rounded to 332. But again, because we're going to use this in the next step, I don't want to round too much, since we're going to introduce some errors. Delta V RMS divided by X sub C, what we just found, 150 volts divided by 331.6, gives us 0.452 amps. That's the current through the circuit. Well, this concludes the first part of the problem-solving session for Chapter 33. Until next time.